explaining the basic transistor switching circuit. It is built using a BC547A NPN transistor. The main purpose of this circuit is to show how a small input voltage can control a larger voltage load. In the circuit, a small supply voltage of 0.8 volt, labeled V2, is connected to the base of transistor through a switch named as S1. When the switch is turned on, the 0.8 volt signal is applied to the base terminal of the transistor. This voltage is enough to forward bias the base emitter junction, causing the transistor to turn on once the transistor between collector and emitter actively closes the switch. The collector of transistor is connected to a 12-volt power supply P1 through a 15 kilo resistor R1. The purpose of the resistor is to limit the current flowing through the transistor and protect the components from damage. When the transistor conducts current from the 12-volt supply flows through R1, then through the transistor and finally through the LED connected at the bottom of the circuit. This current flows light up the LED. The LED serves as a visual indicator to understand when the transistor is conducted. Expert will explain the Silpa.
I am Shilpa. I am going to explain next part. If the switch S1 is turned off, no base current flows into the transistor. Without base current, the transistor remains in the off state, also called the cutoff region. In this condition, no current flows from the collector to emitter, and therefore the LED remains off. This shows how the transistor can act as an electronic switch controlled by a small input signal. The interesting point here is that a very small voltage like 0.8 volt can control larger 12 volt circuit. This is why transistors are widely used in switching and controlling applications. This circuit helps to demonstrate the basic working principle of NPN transistors, especially how base voltage controls collector current. It also explains the importance of registers like R1 for current limiting. Circuits like this are commonly used in real applications such as really drivers, sensors, microcontrollers, outputs, and small automation systems. By using simulation software like multisim, students can clearly observe how the transistors responds to different input conditions and how switching actions takes place in electronic circuits. Thank you.
Hello everyone, myself Srujan. I'm gonna present inverting amplifier part. An operational amplifier is a high-gain electronic device used for amplification of signals. The IC741 is a widely used general-purpose operational amplifier. An inverting amplifier is a basic configuration of an op-amp. In this circuit, the input signal is applied for the inverting terminal. The non-inverting terminal is connected to the ground. A resistor is connected between input and inverting terminal. Another resistor is connected between output and inverting terminal. The resistor provides negative feedback. Negative feedback improves stability and accuracy. The op-amp operates in closed loop condition. Due to the high gain, the voltage difference between terminals is nearly zero. The input current flows through the input resistor. Negligible current flows into the op-amp input. Here, an output voltage is developed across the feedback resistor. The output voltage is proportional to the input voltage. The voltage gain depends on resistor values. Gain is independent of op-amp internal gain. Voltage gain is given by AV is equal to minus R1 by R2. The negative sign indicates phase inversion. The circuit uses dual power supply. Typical supply voltages are plus 15 volt and minus 15 volt. The op-amp cannot reach exact supply rails. If output exceeds limits, saturation occurs. Saturation causes clipping of waveform. Clipping is observed in oscilloscope output. The circuit provides stable amplification, noise and distortion are reduced, the frequency response is good, And here we can observe the inverting amplifier is easy to design, widely used in analog circuits. Okay, thus the inverting amplifier is an important for op-amp application. Next, non-inverting is going to explain by our teammate Varun. Uh,
Thank you, Srijan. Good morning, everyone. Today I'm going to explain the non-inverting amplifier circuit using a 741 operational amplifier. In this circuit, we are applying a sinusoidal input signal of 1 volt peak and 10 Hz to the non-inverting terminal, which is the positive input of the op-amp. Since it is a non-inverting configuration, the output signal will have the same phase as the input, meaning no inversion happens. Next, we have a feedback network made of two resistors, R1 and R2. These resistors from negative feedback from the output to the inverting terminal. The feedback determines the gain of the amplifier. The gain formula for a non-inverting amplifier is gain is equal to 1 plus R1 by R2. So the output signal is approximately 11 times larger than the input. The op-amp is powered using plus or minus 15 volts supply, which allows the amplifier to handle AC signals properly. As we observe in the oscilloscope, the white waveform is the input and the red waveform is the output. The output follows the same shape as the input but with a much higher amplitude, clearly showing that amplification has taken place. To conclude, a non-inverting amplifier increases the amplitude of the input signal without changing its phase and uses negative feedback for stability and controlled gain. Thank you.
Varun?